Okay, so good morning, everyone, or good afternoon. Depends which time zone you are in, or maybe even good evening. So today, our third day of the workshop. So, and our first speaker, Stephen Wright, and Stephen will talk about optimization in data science. So, Stephen, please, you can start now.
Sure. Okay, let me share again. Great. Okay, so I hope you've had a good workshop. I would have come to more of it, but I forgot that I was a day earlier here than you, so I missed out on the first day altogether. So sorry about that. Okay, so this is a talk. I've given versions of this talk for the last 4 years, but I've just been overhauling it pretty thoroughly. In fact, I was just writing new slides for it 5 minutes before I came on, because there's just a ton of new developments all the time in the way that optimization is being used in data science. There's really no end in sight to the kinds of contributions that we can make as a community. So let me start out by giving some context. I can sort of skip over this stuff pretty quickly because I think most of you are fairly familiar with this. I then got this laundry list of 13 problems in data science that you can write as continuous optimization problems. So I'll go through those, but then I'll get to stuff that's probably more current and relevant and represents ongoing research. So these are all things at the interface of machine learning and optimization. So I'll talk a little bit about benign non-convexity. That's this phenomenon that's been observed recently, that there are a lot of problems in machine learning that are non-convex, but are actually easy to solve. I'll talk about some of the optimization issues that arise in deep neural nets. And the fourth one of those, neurotangent kernel, nonlinear least squares, that's the thing I was just adding some slides about. I'll say a little bit then about adversarial machine learning, which is a really good use case for robust optimization. And then I've just got a slide or two at the end about reinforcement learning, which of course is another really hot area these days and also ties into optimization. Okay, so data science, this is a term that's become a little bit of a catch-all term that sort of encompasses AI, machine learning, data analysis, statistical inference. And, you know, you've all heard this term, it's being used everywhere. There are new degree programs in data science, there are centers in data science popping up all over the place. And I sort of see, I see it as having two aspects. One is to extract meaning from data. Usually we've got large collections of data and we're trying to learn stuff from it. Like we're trying to learn important features, or we're trying to learn about fundamental structures in the data. And the second thing is to use the knowledge from that process to make predictions about future similar data. You know, so glean kind of important features or facts or knowledge that we can use to put to good use in the future. So it's a very interdisciplinary area. There are foundations in statistics. In fact, some people in statistics like to say we are data science, but it also brings in lots of computer science. AI is a field that sort of had its roots in computer science. Machine learning has been around in computer science for decades. Then there are also these systems aspects like databases, parallel systems, and even GPUs. So it brings in architectural issues as well, because training neural networks is an extremely compute intensive process. So there are now chips designed specially for that purpose. And the theme of this talk is that optimization provides a lot of important tools in modeling, formulating, and solving these problems using algorithms. And then there are in certain areas of data science, there are very close ties to the application. So when you're dealing with signal processing, where the signals can be speech, they can be images, they can be natural language, the techniques, the data science techniques are very customized to those applications. And then robotics is another area where there's a lot of highly customized data science going on. And just a note before we really dive into this is that, you know, there's a tremendous job market in data science, but the vast majority of people that are working in industry and data science are not doing the kind of thing that I'm talking about here. What they're really doing is sort of cleaning and preparing the data, getting data sets into a state where you can actually do analysis on them. And to do the analysis, they often just call standard packages and often use very standard techniques like, linear least squares and logistic regression. And often it's nothing very fancy, or they use deep neural nets because they're very easy packages that you can use to do that. But most of their effort is in just getting to the point where they can call a package. Okay, so defining a little bit of notation, which I'll stick with for most of the talk, not all of the talk. I'm going to mostly consider the case where the data set is a finite set of M objects, where each object consists of a vector of features, and I'll assume it's just a real vector, AJ, and where J goes from 1 to M. And then also there's something that we'll call a label or an outcome or an observation called YJ that's associated with the AJ. The YJ could be a regression, it could be a real number, and that's a regression problem where we're trying to match the AJ to the YJ, learn how to predict YJ from the AJ. The YJ could be a label. It could tell you that the object that you're looking at that's represented by the feature vector belongs to one of M classes. So it could be one of M sort of different kinds of objects. It could be a label. There could be multiple labels. You could be classifying the AJ according to a number of different criteria. There are also lots of interesting problems where there is no YJ. There are only AJs. You've just got collections of feature vectors. But you can still do interesting things with those. You can sort of figure out that most of the AJs lie in a low-dimensional subspace. So each of the AJ might be a vector of length n, or n could be in the millions, but they all might be approximately in a low-dimensional manifold of, of dimension 3 or something. That could be also not a subspace, but a manifold. It could be a nonlinear, a nonlinear manifold. Another thing you want to do with AJ is clustering, and they're still very popular problems where you can sort of associate each AJ with a cluster and posit that each cluster represents some sort of commonality so that the AJs in a cluster are alike in some sense. So then figuring out how to group the AJs into clusters is, a problem that's been around for a long time. So fundamentally, what we're trying to do in data analysis is to learn a mapping from the AJs to the YJs. And even when you're talking about clustering where there are no YJs, there's still, in a sense, a mapping. You're trying to map the AJ to its associated cluster, in a sense. And you're looking for the function phi that does that mapping. That's essentially what the whole field is about. And you might also want phi to satisfy additional properties that make it, in some sense, plausible or reasonable or generalizable to new data that's not in the actual training set of AJs that you're working with. Now, usually, I said here phi j is a function. Functions are very, they're infinite dimensional objects. So in order to turn this into a tractable problem that you can actually compute with, you can often define the phi in terms of some parameter vector x, where x is finite. And so, the x together with the AJ defines the output of phi. And so that turns it into a data fitting problem. You're looking for a nice x such that phi of AJ parameterized by x gives you approximately the YJ that you're looking for. And the objective function, so this is where your optimization problem is starting to emerge. You're trying to sort of capture the difference between phi of AJ, x, and YJ. You can capture that in an objective function. You've got one of those for each value of J, so you can just add them all up. And often you get a very structured objective function. It's got the so-called finite sum structure where it consists of a sum of M objects, each of them being this loss between phi of AJ and x and YJ. So the process of minimizing that objective function and finding the best possible x is called learning or training. Usually that's, the jargon that's used for that. So going back to, the function, or what's the purpose of data analysis, once you've learned x, once you've figured out what the function phi is, it does a good job of mapping the AJ to the YJ, you can use it to make predictions about future data vectors AK. So if I come along with another AK that has the same structure as all the AJs, I can just plug it into this function and plug in the X that I figured out from training and get a prediction YK that is, you know, the label that I predict AK is going to be associated with. So that's where the prediction comes from. And also you can do some analysis. You can look at the X, you can look at the phi that's, you know, given by the X, and it will reveal some structure in the data. It might uncover structure like clusters, subspaces. It might also tell you which components of the vectors AJ are important in predicting the output YJ. It could be that you don't need every base pair in a genome to predict whether a person is going to get some hereditary disease or not. There might be only an extremely small subset of base pairs that makes that prediction. And the X could reveal what that subset is, for example. This is a picture that I started showing about 3 years ago. I did a Google on, cheat sheets for machine learning. And I checked it again about a year ago, and it's still there. And I think it's still, I checked it again this year, it's still there. It's on the SAS website. SAS is a software company that provides numerical software optimization software, data analysis software. And the purpose of this is that you can, you've got a data science problem, and sort of what you want out of it, but you're not sure how to formulate it and what tools to use. And this is supposed to be a cheat sheet or a flow chart where you can ask questions about what you're trying to do, and you end up at a node where it tells you what kind of problem you're working with and what kind of algorithm is relevant to that problem. And what struck me looking at this was that the sorts of techniques that were used were, in most cases, are optimization techniques. So the yellow ones that I've circled there, principal components analysis, linear regression, logistic regression, neural networks, basically all of those things, involve optimization in some way. Even the ones that are about singular value decomposition, you might say, well, that's a linear algebra problem. But often you don't just want to do a straight SVD in doing data analysis. You'd want to do some sort of fancy version of SVD where you have to write it as an optimization problem. And the red ones were ones that aren't necessarily optimization, but even some of those, you can formulate them as optimization problems, like random forests. The Dimitris Bertsimas at MIT, has a mixed integer programming formulation of random forests, for example. So even arguably, some of those are optimization problems. So the theme is that optimization really plays a very important role here. Okay, so let me start running through this list of 13 optimization formulations. I won't talk much about algorithms here at all. I'll just talk about how you start with a data science or data analysis problem and how you write it down as an optimization problem. And the one that you've got to start with is linear regression or linear least squares, because this is now more than 200 years old. It goes back to Gauss and Legendre. And to put it in the language that I've talked about this function phi, I've talked about this parameter vector x. You can write linear least squares in that form. You can say that the rows of the matrix A are the feature vectors AJ. The right-hand side Y consists of the outcomes YJ, and you're looking for linear combinations of the elements in each row that predict the YJ. And you sort of judge how closely the AJ transpose X maps with the YJ by just squaring the difference between the two, and then adding up those squares and finding the X that minimizes that sum of squares. That's what that field is all about. And it's a data analysis problem. And it fits in the framework that I've just been talking about. Now, you can do all sorts of things to enhance this. So this idea of Tikhonov regularization goes back some decades now, where you look to sort of find a slightly more, regular X version of X, where you sort of suppress the norm a little bit, the 2 norm. That makes it a little bit more stable, the perturbations in the right-hand side Y. Noise, in other words, noise in the observations. Another thing that's been very popular in the last 2 decades, or at least 15 years or so, has been to use L1 regularization. Actually, this goes back to Tibshirani in 1997, but it got really popular during the compressed sensing era, because it's known that adding on a small multiple of the 1 norm tends to give you a solution for X that's sparse. It only has a few non-zeros in it. So that's an enhancement of linear least squares. Now, there are all sorts of other enhancements of linear least squares where, first of all, you can replace the least squares loss by some other loss that captures the discrepancy between AJ transpose X and YJ. And you can also change the regularization function from the square in Tikhonov regularization or the lasso, which is the one norm. There are all sorts of other things you can use there. For example, you can use a Tukey byweight function. This is just one of many possible examples. This one behaves like least squares when the discrepancies, the residuals are small, but it flattens out. As the residuals get large, it just asymptotes at being 1. So this has the effect of sort of ignoring the outliers. They don't affect the solution very much. So if some subset of the data has, egregious errors in it, they don't throw the solution out as much as they do if you're using a least squares loss. And then there are also different kinds of regularizers you can use that sort of behave, in some sense, some of them are like L1, but again, they flatten out when the X gets larger. So in other words, they're not thrown out by large components in X. And there are all sorts of statistical analyses of when different loss functions and different regularization functions are useful and have good statistical properties, good robustness properties, and so on. But all of them end up being optimization problems, and you can write them down in exactly this form and minimize them over X. And there are some challenges there because they're non-convex and they're non-smooth, and so that throws up some interesting issues. But we sort of know how to deal with those. Okay, the third one is in matrix sensing, and this is, in a sense, is an extension of linear least squares to the case where the X is now a matrix rather than a vector. So now the story is that you're trying to figure out what X is, what this matrix is, by probing it using a bunch of linear operators AJ. So by linear, I mean the AJ is some linear combination of the elements of the matrix X. And from that, you're getting a YJ. So you know what AJ is, you know what YJ is. You're trying to reconstruct what X is from M of these observations. And so you can write that down again as a least squares problem. In fact, because all these things are linear, this is exactly a linear least squares problem. But the twist here is that often you know some additional information about X. So for example, you might know that X is low rank. In other words, it's the outer product of two sort of skinny matrices. And using that additional information, you might be able to find a low rank X that matches these observations. And there are different ways to do that. The original way that generated a lot of excitement, sorry, I don't want to jump to the bibliography, was in this paper of Wright, Fasel, and Perillo in Science Review in 2010, where they just took this least squares loss and they added on what's called a nuclear norm term. The nuclear norm of a matrix is just the sum of its singular values. So what they got was a problem that looked a lot like L1 regression, which was this problem here. It looked like the extension of L1 regression to the matrix case. And they're able to show that by minimizing that, it gave them a solution X with low rank because it zeroed out most of the singular values. But more recently, there's been a lot of interest in not doing that, but rather explicitly writing down the X as a low rank matrix, explicitly expressing it as the outer product of L and R transpose. And the problem with that is and then minimizing over L and R to match the data as well as you can. The problem with that is that this problem is non-convex. It's individually convex in L and R, but jointly in L and R, it's not convex. And so it was thought that, okay, for a long time, it was thought, well, that's a bad thing to do. We really have to work with the original space. The problem is this original X is much bigger than the total number of elements in X is much bigger than the number of elements in L and R combined. And so this formulation is much more compact, even though it's non-convex. But recently it's been realized that the non-convexity actually isn't that bad, that under certain assumptions on the AJs and on the number of AJs, this problem is actually easy to solve, even though it's non-convex. And that was realized, I started noticing that about 10 years ago, that these problems actually were not hard to solve. you always seem to find the global minimum from pretty much any random starting point. But it's only in the last few years that people have started to understand why that's true. And I'll say more about that later on. Okay, the fourth application is sort of similar. It's non-negative matrix factorization. This crops up a lot in a bunch of cool applications. I've mentioned a few of them here: computer vision, document clustering. So again, the story here is you've got this matrix Y, which can be fully observed or sometimes only partially observed. And you're trying to express it again as a low rank matrix, as an outer product of two skinny matrices that only have R columns each. But the additional twist here is that these have to have non-negative entries. And that turns out to be important in various applications like this. And so the algorithm that people have used for this for, I don't know, the last 20 years at least, has been alternating minimization. So they've fixed the L and they've solved a bound constrained linear least squares problem to find R. And then they fixed the R and solved a bound constrained linear least squares problem to find L. And they've just gone back and forth like that, vice versa. And that works pretty well, okay? And again, it wasn't really understood until recently why that works well. I think there's now some sort of theoretical understanding of why that's the case. And there are a lot of variations of this problem. I came across one in genomics, I guess last year, where the columns of L had disjoint support in this genome clustering application. It had this additional property apart from this non-negativity property. Okay, number 5, recovering dependency networks. This one is really quite cool, I think, and it's been around for about 15 years. And in this one, you're dealing with a random variable Z, which is a vector random variable with zero mean, let's say. And you've got multiple observations of Z. And so you all know if you've got multiple observations of a vector random variable, you can form a sample covariance matrix, and here it is here, okay? And that will sort of show you the correlations or the covariances between different components of this random variable vector. So, okay, so what you're trying to do is to identify the components of Z that are conditionally independent. So it could be that this covariance matrix is dense, which means that there are correlations between every pair of elements of Z. But it could be that the structure is actually more interesting than that. It could be that element I influences element J only because I influences some other component K, which then influences J. So there could be sort of a chain of dependencies linking I and J, but they're not actually directly influencing each other. So the question becomes, how can you uncover that chain of dependencies? And it turns out you can do that by taking the inverse of S. And there's sort of interesting statistical reasons why that's true. And so you might have, by taking the inverse of S, you get a matrix X, which might actually be sparse. And the locations of the non-zeros in X will tell you the direct causality or the direct influence of different components of Z, that different components of Z have on each other. So for example, if you've got a six-dimensional random variable, its inverse covariance matrix maybe has this non-zero structure, that's inferring that there's this pattern of dependencies between the components of Z. Now, if you take the inverse of X to get S, you'll find that S is completely dense. So there are correlations between every pair of elements of Z. But in fact, the way that they directly influence each other is much more sparse and much more interesting. Okay, now the problem is that you can't just directly invert S to get X because you've only got a finite set of observations, so you don't have a clean, exact covariance matrix. All you've got is this sample covariance matrix. And so you can make an optimization problem, which is basically give me a sparse matrix X, which is approximately equal to the covariance of S, but also is sparse. So you can write it down as this sort of regularized optimization problem, where you've got this term added on here, which enforces sparsity in X. Now, if I left this term off, and just minimize these first two terms with respect to X, I would get exactly that X is equal to S inverse, okay? So these are the terms which sort of makes X close to S inverse, and this is the term which makes X sparse. And the bigger I make lambda, the sparser X is going to be. Okay, so this is, I think, a very cool application that's, yeah, that, you know, where the optimization is really critical in figuring out what to do. Okay, here's another one that's got historical interest because Dasbremont and Michael Jordan and their co-authors won a Best Paper Award for this in 2007. And it was really one of the first times optimization had been used in data analysis involving matrices. And again, they're dealing here with sample covariance matrices. And what they're looking for is sparse principal components. So what they're looking for is approximations. By the way, these matrices S are symmetric, of course, being covariance matrices. So they're looking for vector Z, which are close to the maximum eigenvectors for S, but which are also sparse. So in other words, sparse principal components. That's to use statistical jargon. And what they figured out was that they could write this as a semi-definite programming problem. They could come up with a convex relaxation. If you write it strictly the way they want to solve it, it looks like this. And this is not nice because this constraint here is a constraint on how many non-zeros V is allowed to have. And so that's a difficult constraint to apply unless you're prepared to use integer programming. But what they found was that they could come up with a convex relaxation of this as a semi-definite programming problem. And by manipulating, so they could basically use M as a proxy for VV transpose. And by applying you know, appropriate constraints to M, and by applying a norm on the sparsity of, applying a constraint on the sparsity of M, they could end up with an M that could then be factored to obtain these matrices V. And in fact, if they're strict enough with the sparsity here, they can actually force M to have rank 1. And so then M will actually have this form VV transpose. So they came up with this sort of positive semi-definite programming proxy for the problem they really wanted to solve. And so this was a, you know, this was a paper that got a lot of attention at the time because it showed that, you know, interesting optimization tools could be used to solve these, you know, important problems in computational statistics, data science. So there have been extensions of this lately. It turns out there are interesting problems in video processing where you've got a matrix Y and you know that it's a sparse plus, it's a sum of a sparse matrix and a low rank matrix. So this turns up in video processing. If you've got, you know, a bunch of video taken over many hours and you've got 24 frames of video per second, essentially you can decompose it. Most of the time, you've just got this boring background going on, and that's represented by the matrix M. And then the low rank part of the video is the matrix S, and that's the interesting stuff. When someone walks across the frame, that can be represented as a low rank matrix. And so the video, the whole collection of video is Y, and you can break it down into the background, which is a low rank part, plus S, which is a sparse part. I'm sorry, maybe I said S was the low rank part. S is the sparse part. And so you can solve a problem like this, where you can use that nuclear norm to force M to have low rank, and you can use the one norm to force S to be sparse. And you can you know, solve it that way. You can also do what I did earlier, which is to replace this nuclear norm with just an outer product of these two skinny matrices, L and R, and you can write it as this non-convex problem instead. And solve it this way. So this has been around for about 10 years. I remember I visited Rice in 2012, and we talked about follow-ups to this kind of problem. Okay, subspace identification. This was something I worked on with Laura Balzano in 2014, 2015. And this is an example of clustering where we've got a bunch of matrices, we've got a bunch of vectors AJ, and we know they all approximately lie in a low dimensional subspace. But the twist is that we don't know all the entries of AJ. There's a bunch of missing entries in AJ. So nevertheless, we're trying to identify a matrix X which spans, whose column space is the subspace that all of the AJs approximately lie in. So this has this cool application in structure from motion. which is a thing in computer vision. In fact, we wrote some papers with some application people after 2014 where we did experiments involving a toy dinosaur. And what you're doing is you're observing a 3D object from a bunch of different angles, and it's an opaque object. So you can paint reference points on the surface of this object, but when you look at this object from any angle, you can only see a subset of the reference points. You don't see all of them. And when you rotate it and look at it from different angles, you see a different subset of reference points. Now, every time you look at this 3D object from a 2D angle, of course, you're doing a projection onto a low-dimensional space. And there's this classical theorem in computer vision that's, I don't know, 30 or 40 years old, that says that by figuring out a spanning set for these low-dimensional projections, you can actually locate all of the reference points in three-dimensional space and thereby reconstruct the 3D object. And so we've actually done that for real data arising from structure from motion. Okay, so getting into stuff which is going to become more relevant when I talk about deep learning, and this is linear SVM. This was a classification problem that was maybe the first one. It goes back a long time, back to the Mangasarian was solving these problems in the early 60s. So this is a problem where each item of data, each of the AJs, belongs to one of two classes. So we label the YJs are either +1 or -1. And you want to be able to predict the label by a linear combination of the elements of AJ. So much like least squares, you define X to be the vector of coefficients that you use to form a linear combination of the AJs. And you also define beta to be some sort of shift that you apply to AJ transpose X. And you want to choose the X and the beta in such a way that when AJ transpose X minus beta is bigger than 1, that predicts the label is +1. And when it's less than -1, that predicts that the label is -1. So in other words, this function phi parameterized by X is basically just the sign of AJ transpose X minus beta. I guess beta is also a parameter here. I should have put beta as additional parameter here. So you can write that as an optimization problem by basically writing down this loss function. And if you look at this loss function long enough and hard enough, you'll figure out that if X and beta are doing a correct classification, if one of these two things is true, then this loss function is going to be 0 because this first term is going to be negative. And so when I take the max of that first term and 0, I get 0. However, when these conditions are not satisfied, the resulting loss is going to be positive, okay? And so by minimizing this loss function, I'm trying to find an X and a beta which make the sum over all of the training terms 0, if possible, or if not, as small as possible, okay? So if I can make it 0, it means I'm correctly able to classify all the objects. If I'm able to reduce it to something small but non-zero, it means, okay, a few of the objects are not going to be correctly classified, but most of them are. So we can draw a picture of this, and I'm sure you've seen pictures like this before. I've denoted the two classes by red and blue, and the plane, the line here is defined by X and beta. The X gives you the slope, the beta gives you the intercept. And so this particular choice of plane is correctly classifying these two classes of objects. Now, this is an illustration of something that's going to become important later on, this concept of generalizability, because in statistics, often when we're talking about machine learning, we're viewing the training set as just a finite sample from two underlying data sets that we really want to be able to classify. And the two underlying data sets are represented here by these red and blue or pink and blue blobs. Okay, so that the data that we're given, which are the red and blue dots, are just a finite sample from that set. And so our goal might not be just to separate the finite sample that we're given, but to come up with a solution that will also do a good job at separating the data that we can't see, that is the data in the red and blue blobs. And so we might actually be looking for a better solution, that is this line here. This again will correctly classify the finite set, but also does a good job at separating the red and blue dots. And I could have sort of figured out how to do that without knowing how the red and blue dots are. I could have said, give me the solution that not only separates these two sets, but also is as far away as possible from each of the two sets. And that would have given me the solution that sort of goes down the middle, the channel in the middle as much as possible. Intuitively speaking, that's likely to do a good job of separating even the data that I can't see. This is what the picture looks like when I can't perfectly separate the data. So I can separate most of it, but you can see there's a few items of data that are on the wrong side of the plane. And that's, of course, going to happen in real life when we've got data that's not perfectly separable. Okay, kernel SVM. So this is a generalization of SVM where I take the data vectors AJ and I apply some transformation. I lift them into some high dimensional space. So it could be that the AJs by themselves are not linearly separable. But when I lift the AJs, when I expand their dimension, when I do all sorts of weird combinations of the components of AJ and lift it into a high dimensional space, it could be that then I get something that's linearly separable. Okay, that's the idea of how kernel learning comes about. It's one way to motivate it. Now, here is the learning problem that I wrote down earlier on the 2 slides ago, or three or four slides ago. I've added on a regularization term here, which is the term that gives you the X that sort of goes down, separates the two sets as much as possible. Now, there's a very, very nice observation that was made in the 90s by people in machine learning, which is that if you write, this problem is actually a quadratic program, and it's a convex quadratic program if you formulate it right. And you can take the dual of that convex quadratic program and you get this problem here in a completely different set of variables. It's also a quadratic program, and the elements of the matrix, of the Hessian matrix in that QP, turn out to be inner products of these transformed feature vectors given by this psi of AJ. So they made that very, very nice observation, and they call this matrix a kernel. And they noticed that, well, you actually don't need to know what the psi is. All you need to do is to be, in order to set up this dual problem, is you need to be able to evaluate the Q. And in order to evaluate the Q, all you need to know is the ability to evaluate these inner products. So they said, let's not bother about defining psi. Let's just define a function, a kernel function K, where I can plug in 2 feature vectors and get an output, which then gives me an element of this matrix. And then when I solve this problem, I get a solution alpha. I can use that to make predictions about new feature vectors A, simply by plugging A into this kernel matrix and doing some manipulations involving alpha. I'm not going to go into that. But anyway, this was a really, really neat use of convex optimization duality theory in a classification setting that was invented by people in the machine learning community. And before deep learning came along, this was kernel SVM was the way to go. It was the dominant technology until the last maybe 8 or 10 years. Okay, multi-class logistic regression. This is sort of an extension of classification where you've got multiple classes. You don't just have 2 classes, but the object you're looking at could belong to one of M classes. And in the case of image classification, M can be really big. It can be, in the hundreds or thousands. And what you're looking for is not a prediction about which class the object belongs to, but a set of odds. So you want to be able to make a prediction. If I give you a feature vector A, you'd like to come back and say, okay, there's a 76% chance it's in class 10, there's a 20% chance it's in class 2, and there's a 4% chance it's in class 103, and a negligible chance that it's in any other class. So it turns out you can set up this logistic regression problem whose solution will give you a bunch of functions that are able to make those kinds of predictions. And I think I won't work through the details here so much, but you have to, it turns out the X's that parameterize those functions, you have to have a separate X for every class. So there's a lot of parameters here. The number of parameters is basically the number of features in the vector A times the number of classes. And you can combine those things in a way that end up giving you these odds functions. And this is the function that you need to minimize to find those coefficient vectors X. It's still a convex problem, surprisingly enough. I think I'll skip this one, atomic norm regularization. This was a generalization that Wright and Alan Wilsky and Venkat Chandrasekaran and someone else came up with around 2010, which was sort of a generalization of compressed sensing and low rank matrix completion and a bunch of other problems in signal processing. Basically, they said, look, there's an awful lot of problems here with a common sort of structure. And the structure is that I'm trying to minimize some function, but the objective or the unknown vector that I'm trying to identify by doing that minimization is a combination of a small number of fundamental of atoms, fundamental objects from some set A. So Z itself might belong to a very high dimensional set, but I might be looking for minimizers F or approximate minimizers of F, where the Z's are just a linear combination of a small number of fundamental elements. So in compressed sensing, for example, these fundamental elements are just vectors with a 1 in one location and zeros everywhere else. They have a very natural definition. When Z is a low rank matrix, then each of these elements A, each of these fundamental elements could be a rank 1 matrix. And so Z will just be a combination, linear combination of a few rank 1 matrices and so on. So they identified a whole bunch of common problems with that sort of structure, and they came up with a common way to express them and to write down objectives that will give you the kinds of solutions that you're looking for. Notice that this looks a lot like that L1 penalized least squares problem that I mentioned right at the start, back in the first or second application. The last one is community detection and graphs. This has got a lot of, Facebook solves problems like this all the time when they're trying to figure out relationships between people on their network, the billions of users on their network, and how they form communities of common interest. You can write that down. I'm skipping all the details. In fact, all I'm saying here is I used to have a bunch of slides on this problem, but it takes too long to explain. You can write down an objective under certain assumptions where you're able to identify that this set of nodes is, they're interacting with each other quite often. This set of nodes is interacting with each other quite often, but the interactions between these two sets are relatively rare. And you can write down an optimization problem, which under certain circumstances is able to give you the answer to that. Okay, so let me get into some of these issues in the time I've got remaining, some of these issues of current sort of research interest. The first one, I gave a talk at WICO 3 weeks ago, and I dwelt on this in some detail. I think a lot of you were at that talk as well, so I'll skip over it a little bit more quickly here. This is something that's cropped up in the last 5 or 6 years, as I said, where people are discovering that a lot of non-convex problems that crop up in machine learning, you can actually just apply local optimization, very standard optimization methods to them, gradient-based methods, and they'll find global solutions, or they'll find at least solutions that are close to global solutions or that are interesting in some way. So these show up in matrix, low-rank matrix and tensor problems. They show up in random phase retrieval problems, in neural nets, and I'm going to say a lot more about that, AC power flow. And I found this page of Ju Sun, who's keeping a list of all of the literature in this area, and he's keeping a laundry list of all the new problems that are showing up that have this benignly non-convex structure. And I'm not going to get into the details of what properties these problems have, except that there's sort of a list of 5 or 6 common properties that you can prove about certain instances of these problems that give rise to this nice benign, this benignness. So they could be properties, and they're not, each of these applications has 1 or 2 of these properties typically. They don't have all of them. So some of these problems have applications that all the local minima are actually global minima. They all have the same objective value. So as long as you've got an algorithm that finds a local minimum, you can solve the problem. Another one is a property that all saddle points are strict saddle points. So a saddle point is a point with 0 gradient, but that's not a solution. And some of these problems, you can show that if you're at a point with 0 gradient that's not a solution, then if you look at the second derivative matrix, the Hessian, it's got a direction of strictly negative curvature. And by moving along that direction, you can get away from the saddle point. So that's a property that your algorithm can exploit to avoid saddle points. Another one that's very common in matrix problems is that very often you can come up with a smart way of finding an initial point x naught that you can guarantee is in a neighborhood of the solution. So if you start from that initial point, you can then just apply gradient descent and you can go to the global minimizer. So they've got properties like that. Here's an example of I think I'll skip over that, matrix sensing, which is maybe one of the simplest problems that has this benign non-convexity structure. Okay, but let me get into talking a little bit about deep learning, since that's something that a ton of people are interested in. So here's a picture of a simple neural net. This is a convolutional neural net, completely connected one, where you input a feature vector at the bottom. So the thing you're plugging in at the bottom is one of these vectors AJ. What comes out at the top is often multiple outputs. That's the blue line here, but these can be combined into a single output. You can take these and do what's called a softmax on them. You can do a linear combination and combine them to get some sort of a scalar output. And that could be the label YJ, the thing that you're trying to predict. But in between the bottom and the top, there's this, nonlinear, very systematic, kind of simple nonlinear transformation that's going on. At least it can be expressed in a simple way, but it ends up being quite complicated. So typically what happens between layers is that you take the output of one layer, you multiply it by a vector W, you add some offset B, and then you plug it into the next layer, layer L+1. Then within the layer, you do some sort of a tweak that's captured by this function sigma. And the most common thing that you do these days is simply the ReLU operation. You just take the input to that node and replace it by 0 if it's negative. Otherwise, you just leave it alone. Okay, so you're essentially doing a composition of a bunch of linear transformations with a bunch of these very simple ReLUs or very simple element-wise operations. So that's what's going on as you move from the blue layer, the red layer, to the blue layer. And then what happens at the last layer is just some sort of linear combination. Now, there are many enhancements and variations of the neural net that I showed you on the previous slide that are sort of suited to certain applications. So there are cases where the connectivity is restricted. There are cases where you put constraints on the elements of W. You might add some sort of penalty term. Another one that's been very popular lately is that you add extra connections here so that the input to a layer doesn't just come from the previous layer, but it also comes from the layer 2 layers down. So layer L, in other words, has inputs from layer L-1 and L-2. And that turns out to be advantageous. It actually turns out to be easy to analyze in some sense as well. That's called a ResNet. And then there's LSTM, which is useful when you've got sequence data and so on. Okay, but the thing that I showed you is kind of, good enough to talk about. Now, how does this sort of fit into the framework that we've been discussing? Well, it matches the framework in that, again, we can still, basically these weights, these transformations that take you from layer to layer, they are the X. They are the thing that parameterizes the function that's mapping the AJ to the YJ. And you can write down a loss function that captures the error in that prediction, that takes the AJ, that passes it through the neural net defined by X, where X is this collection of W's and B's. It comes up with some output, and then it compares it with YJ. And then you do that comparison and you write down an objective which tells you how well you did at predicting the YJ output. And that gives you this loss function H. And then you sum up or you average the losses over all the training data, and that's the thing that you want to minimize to find the optimal weights, X. Okay, and this is exactly what they do in training neural nets. Now, of course, the dimension of X here is huge because the number of training, you add up all the elements in the WLs and the BLs, it can be in the billions or nowadays trillions, literally trillions. And in fact, the number of elements now usually exceeds the number of items of data in the collection. So often the items of data in the collection run into billions, but the number of parameters can nowadays it's in the trillions. And this training function is now, it's not linear anymore, it's not convex anymore, and it's not even smooth. When you're doing this ReLU operation, this is not a smooth operation. But nevertheless, they apply just a gradient type method, stochastic gradient, to minimize L and find the optimal weights. Now, stochastic gradient, what stochastic gradient does is it just picks a subset of these M items in this objective function. So if M is in the billions, it might only pick a subset of 100 or 1,000 out of that complete collection of data. And that gives you a batch BK. And then you just average the gradients over that batch. And you use that as a guess of the gradient of the full function. And you take a step in the negative gradient direction or the negative G direction. And that's how you update the weights. So that's what this famous SGD algorithm is. That's all it is. But of course, you know, doing this in an efficient way on real problems and real nets is, you know, there are literally hundreds of people employed by Google and Facebook and the other big tech firms whose job it is to figure out what's the best way to choose the size of the batch, what's the best way to choose the alpha K, what's the best way to choose the momentum term, which I haven't talked about. This is so-called hyperparameter optimization, and there's an entire industry devoted to doing that. Okay, so there's this incredible paper by Kingman and Barr from 2015 that now has 92,000 citations, where they basically just they take this GK and scale it with a diagonal matrix, and they learn that diagonal matrix by observing what's happening to each of the components over multiple iterations. So they basically look at the size of the GKs over a whole bunch of iterations. They take some sort of weighted average, and they use that to come up with, you know, how the different components of the weights are scaled. So it really is just a diagonal scaling of the GK, and it turns out to really improve the efficiency of a lot of the training methods. Now, this idea of using diagonal scaling, of course, was well known to people in optimization. In fact, you know, people have proposed using the diagonals of the Hessian to give you an approximate scaling and give you sort of a cheap and dirty approximation to the Newton step. That idea has been around for a long time, but Kingman and Barr sort of introduced it into the ML community, and it's become an absolute juggernaut. And there are many variations of it now, and you know, there are even proofs of why it can work. Okay, I've mentioned overparameterization, and this again has, I guess in the last 5 years, has given rise to a tremendous amount of interest, both at the practical and theoretical level. The fact that by making the neural network much bigger than it needs to be, somehow you make the training problem easier, okay? If you just apply stochastic gradient and run the problem of minimizing the loss function L long enough, it will go to a solution that perfectly fits the training data, so-called zero loss solution, provided the neural network is overparameterized. In some sense, you make the optimization problem easier. But statistically, that didn't seem like a good idea. Conventional wisdom in statistics was always that if you overfit to the training data, if you do too good a job at fitting the training data, it's not going to do very well at making predictions about other data that's not in the training set. So this sort of flouts the conventional wisdom. And so there are all these explanations now as to why you can interpolate and still get good generalization. In fact, there's this so-called double descent curve, this idea due to Belkin in the last 3 years, but it goes back a lot further. He sort of explained why overparameterization might not be a bad idea. And he explained it like this. The x-axis here is the complexity of the model. This is basically the number of parameters you put in your function in your neural net or in whatever function you're using to predict the yj's from the aj's. And conventionally, the idea was you would not make the function too complex. You would sort of stop around about here, at the bottom of this U. I'm not sure if you can see my mouse, but you would stop here where the number of parameters in the model was less than the size of the data set, because that gave you a trade-off between the complexity of the model and it gave you a trade-off between fitting the data, the training data, and giving you a function that would do a good job at predicting on elements outside the training set. So it would stop about here. But the overparameterized regime is way out here. And he's saying that as you overparameterize, as you move past this dotted line, you get into a regime where there are actually many models that fit the data, but some of those models are also generalizable. And the interesting thing is that by just doing gradient descent, it seems to identify the models that have good generalization properties. And so there isn't intrinsically a bad thing to perfectly fit the data, as long as you can show that your model is going to one that also generalizes well. And the surprising thing is standard algorithms seem to have that property. So there's been a lot of work in recent years on explaining why that's true. Okay. Now you're going to stop me pretty soon, right, Madam Chair?
Yeah, well, because we have the whole hour of discussion after that, I think it's not a major issue. So you can go for a little bit longer.
I won't abuse, because I know people just stop listening after 60 minutes. So I won't abuse my privilege too much here. But I'll give you some of the newly added slides here. There we go. Since I went to all the trouble of writing them, I may as well talk about them. Okay, so here's some explanation of overparameterization. There are a bunch of different explanations that people have been coming up with in recent years. I'm associate editor of Acta Numerica, and we invited 3 papers from leaders in this area, who are trying to explain this phenomenon from different viewpoints. One of them is Belkin. Another one is a joint paper of Rocklin, Andrea Montanari, and Peter Bartlett. Peter Bartlett's, of course, from UQ. There was a graduate of UQ, was at QUT for a few years. He's now at Berkeley again. And the third one was from Ron DeVore, who's the wavelets guy from USC. And they all have their own perspective on why overparameterization works. But here is one perspective, and I think it accords with empirical observations and also has been, verified in theory. The idea is that as you grow the number of parameters, you don't just have a single solution that fits the training data, you now have a whole manifold of solutions. And in fact, as you increase the dimension, the manifold of solutions seems to grow to fill the space. So you sort of have a picture like this. The blue line indicates all of the values of the parameters where the training data is fit perfectly, okay? And as you grow the parameter space, the blue line fills the parameter space. So what that means is if I pick some random starting point, if I just pick some red dot in that parameter space as my starting point, as my initial value of the parameters, then because the manifold of solutions fills the space, that red dot is going to be close to one of the solutions because it's going to be close to that manifold. And so if I just run gradient descent, I'm going to be able to converge to a point on that manifold. And in fact, that's what happens. You can show both empirically by generating random starting points and theoretically, this actually is something that's really happening. And so, that sort of partly explains what's going on. So the little red line here is the path taken by, say, a stochastic gradient descent method. Now, something that's become cool recently is so-called physics-informed neural nets. You might have heard of this, where people are trying to model fairly complicated systems where there's a certain input at a certain output, but they're saying, let's not assume that we're completely ignorant of how we get from the input to the output, because we know a lot of physical rules that can make that transformation. We're only missing a part of the knowledge. So let's design a mapping where we make use of the knowledge that we have and just use neural nets to sort of plug the gaps in the model. And one very cool application of this that I found out about only last week, I'm here at UT Austin and I'm talking to all kinds of people here. And I talked to some robotics people last week. And they have this model of robot motion planning. So they've got a very good model for how the robot moves. That's based on contact dynamics and the dynamics of how the different pieces move relative to each other. But there are things that they may not know. So they may not know the friction of the surface that the robot's walking on. And they may not need to learn that by observing the motion of the robot over time, looking at how the joints of the robots move, how it's sliding around. They might need to learn the friction from that. And they can use a neural net just to learn the friction part of the model, for example. Now, it turns out if you use neural nets in this way, you need to constrain the outputs of the neural net to satisfy certain constraints. You can't just accept any old YJ coming out of the neural net, because it's not going to make sense in the context of the role it's playing in this overall model. So it becomes really critical to constrain the outputs of the neural net. Now, what that means in the training problem is that you're not prepared to accept any of the solutions that lie on the blue manifold. You want the solutions to lie in certain regions of the parameter space. And so these green, shapes here indicate, in a schematic way, the outputs that I need the solution to lie in. So I'm only interested in the pieces of the blue manifold that lie inside these green sets. So if I now just pick some random starting point, I'm not going to end up, in all likelihood, I'm not going to end up in one of the green sets. I'm going to need to apply constraints. And what these people have observed is if you just naively apply constrained optimization techniques like adding penalty terms, the optimization seems to get lost, because it has to move from this random starting point all the way into one of these green regions. It has to traverse a very non-convex, non-smooth landscape, and they just get lost. They get stuck in a local minimum somewhere. And so it's a very current area of research, is how do you avoid that behavior? And one thing that's been found so far, very, very recent work, this is 2021, and just, in the last few weeks, they found that augmented Lagrangian actually seems to do a pretty good job at helping them find feasible solutions. Another question that I've asked them to try out, they haven't got back to me yet, is what if you use an algorithm that doesn't pick any old random starting point, but insists on getting feasible first? So first runs a preprocessor that gets you into one of these feasible regions, and then tries to fit the data after that while staying feasible. So maybe that will work as well. And maybe you can apply a bunch of other constrained optimization methods here to this setting, and maybe some of them will work. So this is a very active area of current research. Okay, and if you'll just oblige me for a couple more minutes, I want to talk about these slides that I just wrote. And this is this whole idea of neurotangent kernel, which has become one of the ways of explaining why neural nets are so effective and why they're so easy to train. And the idea is, I'm changing notation here just a little bit. I'm denoting the output of the neural net by this function f. I'm denoting all the weights in the neural net by w, and I'm defining xi as the input data. That's what I used to call aj. I'm sorry, I didn't have time to rewrite the notation. So the xi are the feature vectors, the yj are the outputs. I've kept the same notation for the y's, thankfully. And I'm trying to choose the w's in the neural net so that f of w and yxi will give me the output yj. Okay, so I'm going to assume that, I haven't practiced it. I actually did talk about this back in April in an internal seminar, but I haven't practiced it since then, so I've forgotten exactly how I explain this. But the hypothesis is the following, that if this picture that I showed you a few slides ago is true, my initial W, which is the red dot, is not going to be very far from the final W that I end up with. And you can hypothesize, and you can actually prove under certain assumptions that you can think of F as being an almost linear mapping. As I move from W naught, which is my initial guess, to my final guess W, that I can approximate what happens to F, which is the prediction of the new output of the neural net, by this linear approximation. I can linearize it about the initial point. And I've changed the notation here. I brought in this psi vector to represent the gradient of W of F with respect to W. I can approximate the very nonlinear neural net by a linear function of the weights, okay? And it turns out, the moral of this story is that it turns out that what I'm really doing here is using the gradient of the output of the neural net with respect to W. That's really a feature vector. I've taken the X, which is my original feature vector, I've replaced it by the gradient of F with respect to W, and that's given me a sort of a feature vector in this lifted space. And if you go back to what I was talking about on slide 20, back here, this is exactly what I was doing in kernel SVM. I was lifting the AJ, which are the input feature vectors, into some high dimensional space. I was forming a kernel out in that lifted space. I was solving an optimization problem that was giving me dual variables that I could then use to reconstruct the function f. And this is exactly what's happening in neurotangent kernels. You're in this situation with a, let me find it again. You're in this situation where you've lifted the feature vector into this high dimensional space. You can actually write down the training problem. You can write down an analog of the kernel function. You can write down an explicit solution for the dual variables, and you can use that to reconstruct the W, which is the which are the weights that actually give you the predictions of the neural net. And so this is what they mean by neurotangent kernel. You can relate what's happening in a neural net under certain circumstances to this very familiar concept of kernel learning. Now, it turns out that you need to, and Belkin, by the way, is a pioneer in this. He has this, one of these active numerical papers. It turns out that neural nets with a certain structure have this property that they're well approximated by a linear approximation, and the weights don't have to move very far to get from initial point to optimal weights. And for reasons that I don't have time to explain, I did have a few slides on this, but it's a sort of if I refer you to Belkin's paper for the explanation, it's not that complicated. But if you can show that if the neural net has two properties, one is that the output layer has a very large width, let's call it M. And the second is that the way that you get from the output layer to the prediction is by just doing a linear combination of those outputs. If you have those two properties, you can show that that your neural net can be so basically approximated by this linear map. Okay, and people say that you're in the neurotangent kernel regime. Now, this is only a partial explanation of why neural nets are so effective, because it's very specific to this case of a wide neural net with a linear final layer. It doesn't generalize to resonance and all those other things. So, but at the moment, all we have are partial explanations. So, it's a very interesting attempt at an explanation. Okay, I'm going to stop there. I'll give you the slide deck if you want to look at the other things that I didn't get around to talking about. And there's a long laundry list of references here as well. So thank you, and thank you for indulging me for the extra 7 minutes.
Well, thank you very much, Stephen. So thank you. I will now stop recording.
Thank you for stopping recording.